Hi, I'm Dr. Melissa Wilson-Sayers. I'm an assistant professor here in the School of Life Sciences and the Center for Evolution and Medicine in the Biodesign Institute at Arizona State University. My area of research is in studying differences in DNA across people, across animals. Every living thing has DNA in it. And what you might not know is that you can look at it. And so today what we're going to do is run through an experiment where you can extract DNA from living things with items you can purchase in the grocery store. So today we are going to extract DNA from bananas. So should we just get started? Any sort of bag with a zippy top will work, just because you're gonna be mashing bananas in here and you don't want it to get all over everything. One of our bananas, our container for our warm salty water that we'll be using. And so let's first start just by mashing some bananas. But this is the fun part, just get in there, mash it. Just mash it up, probably about a minute. So after that, we're going to fill our cup with hot water and salt. And once you have the salt dissolved in the water, then we're gonna mix that in with our banana mixture. And now we get to gently slosh it around. Okay, and here's the next step where you gotta be careful not to get it too foamy. We're gonna add a half a teaspoon of our dish soap. And now we wanna gently, because now it's got the soap in it, it'll really get bubbly if we're too aggressive with it. Okay, and now we're gonna set this aside and we're gonna get our coffee filter set up with our funnel. And here you want to be careful. If you're a little too excited dumping it in there, you'll get slushy banana stuff coming out because it will take a while. Oh, can you hear that? And now we wait. So now that we've patiently waited for all our banana mush mixture to go through our filter, we have the last and most exciting step, which is adding our isopropyl alcohol. We want to really try to keep the alcohol separate from this mixture because the DNA is going to precipitate or come out into the alcohol mixture. And we'll try to add 2.5 to 5 centimeters or 1 to 2 inches to it. And now we wait. The longer you let it sit, the more separated you'll be able to see the two different parts of it, and sometimes we'll find that you'll see lots and lots of DNA there. Sometimes you will only see a couple small strands, and that's part of science. But those little bubbles are sticking along strands of the banana DNA. Oh, look at that. Oh, this actually, all of this right here is the DNA. It's just kind of sticking there. All right, and so we'll show you some other pictures of experiments that we've done extracting DNA out from bananas and potentially a couple other fruits, where you can see some of the different outcomes that you can expect. Thank you for watching. We do have the description for how to do this at home or in the classroom. We have handouts that you can use. So if you are interested in taking DNA out of the cells from the food you eat, you can play along at home. Thank you.
In 1959, physicists Robert Pound and Glenn Rebka performed an experiment in the Jefferson Physical Lab at Harvard to demonstrate gravitational redshift. It was based on physicist Rudolf Mossbauer's effect, discovered 2 years earlier, that involves the emission and absorption of gamma rays from the excited states of iron nucleuses. Here we have an iron atom's nucleus in an excited state. When it falls to a lower energy level, a gamma ray photon carrying the energy is emitted. Once this photon enters a like atom, it will be absorbed, raising the energy level of the encountered atom's nucleus. The problem is that when the gamma ray is ejected, the nucleus recoils. Because of energy momentum conservation, the recoiling energy reduces the energy of the gamma ray. the gamma ray is no longer a match for the other nuclei, and it moves right through. There is no absorption. What Mossbauer discovered was that if he embeds the iron atoms in a crystal, the recoil is reduced dramatically, and absorption can be reestablished. Pound-Repke used this Mossbauer effect. They placed an emitter at the bottom of a tower in the laboratory and installed a detector 22.6 meters above it. No absorption was detected because gravitational time dilation changed the frequency of the emitted gamma rays, so no energy match existed in the detector. The calculated shift was extremely small, but the Mossbauer effect is sensitive enough to measure it. They adjusted the detector's velocity down until absorption occurred. We get the amount the frequency changed using the well-understood relativistic Doppler redshift equation, just like the Doppler shift in starlight. These results came in within 1.6% of the value predicted by Einstein's field equations using Schwarzschild's metric. Although this experiment did not produce new results, it showed that gravitational time dilation, one of general relativity's most significant findings, was consistent with all physical conservation laws. This gave the general theory of relativity 3 successes out of 3 tests.